Hello everyone, my name is Josip, I'm Head of Solutions at Memgraph, and today I'm going to explain to you how you can query your Memgraph if you have a cybersecurity dataset using a simple dataset that we have made that describes us Python vulnerabilities in packages. So here we have connected to an empty Memgraph instance, and if you look at the datasets, we have actually recently added Python dependency vulnerabilities. We can load the dataset, and after that, let's inspect our graph. We can see 284 nodes, 158 relationships, and here is the consumption of Memgraph in RAM. Graph schema is a pretty simple one. It has actually a node called dependency, which can depend on another dependency. There is, of course, a Python package, which can have like its dependency packages, and as we can see, we have two properties, name and version. And one package can be also linked to like has vulnerability, which has the name of the vulnerability, status, description, minimum version of the package, maximum version of the package which is affected. Yeah, so let's go to our query collection. I have here prepared a query collection, which is like a library of queries which you can show to your peers, colleagues, build your own queries and show it to make like a cohesive story. So if actually I query this and I have my graph style editor in place, I can actually run the query, and which displays to me all the Python CVs, and they're all like colored. They're all with a picture of a bug or something. So yeah, but like this is not some query which you'll pretty much use. You need some insights to actually query. So let's list all GQL Alchemy dependencies of 2 hops. So since Cypher is actually a pattern matching language, we can match easily a dependency that depends on another dependency that depends on another dependency, and these two edges will then make sure that they're not the same, so you don't actually end up in GQL Alchemy again. What's GQL Alchemy? It's our own object graph mapper, so it's actually an example revolving around our own library. In relational databases, you would essentially do a join here, but since you are in a graph database and it's an in-memory graph database, so we actually utilize pointers to gain constant time complexity jumps from one node to another. We can actually gain quite an advantage in terms of speed. So here on the if I actually make the full screen, we can see all the 2-hop dependencies from GQL Alchemy to like the ADLFS and Azure Data Store, and then we have Docker, WebSocket client, and requests. Of course, these go to multiple hops, but this is only like 2-hop neighbors. So this is one way of doing it, but maybe we can do it using BFS, and BFS is our own inline Cypher syntax. We have many algorithms, and you can actually, here this query says, okay, give me from GQL Alchemy using BFS all the 2-hop neighbors. If we run this, we get exactly the same results, and I don't have actually my my style editor in place, so I'll just do it like this, and now we have it again. So yeah, regarding these path filterings, I will go now through a lot more just than BFS. So let's say we want to go through all the dependencies that go through Docker. So now we actually don't have before we had like .2, which is 2 hops max. Now we don't have anything, but for every path we find, we want to check if any of the nodes is Docker. And then what we get? We get the graph results that actually here is GQL Alchemy, then Docker, and then it goes to requests and traverses later. However, this part of filtering happens only after we have extracted all of these paths P here, which maybe can sometimes in bigger datasets be troubling, because we might want to filter inline this query so we can get more accurate results, and so that we can yield less paths, and so that we can filter less here. So what we're gonna do is actually use inline path filtering, and this is a feature that's just when you go with BFS. When you want to traverse, you have a relationship, you have a node, and you have a path, and then you can actually query queried by nodes p1 name is Docker. What that means that actually the second node is Docker, and then we will actually get the same results. So yeah, that's basically it from these inline built graph algorithms. We have documentation page. We support DFS, BFS, weighted shortest path, all shortest paths, and then you can do multiple things like filtering by relationship or nodes. You can filter by hops. You can filter by the path that you're currently traversing. So it's actually really powerful because it's inline and it's all executed in Memgraph. You don't need to do any post-application processing. So yeah, let's go back to the query. Get all dependencies of Docker using Memgraph Mage models. So Memgraph Mage is an open source collection of graph algorithms which we can build, and it is built on top of a thing that's called a query module. Query module is essentially this part of the query. It says call graphUtil.descendants and then yield something. It's a piece of code written in Python, C++, Rust, or actually any other programming language that you might want to embed into Memgraph. It communicates with Memgraph as a graph storage via an API, and you can actually transform your inputs, actually analyze it and yield outputs, and return back to your query in the same transaction. So actually how a query module looks like, essentially like this. So you actually start your query, mid-query in the same transaction you start execution of code because you have a runtime that's available to you or Python interpreter. Then you actually exit with the API with the results you got by actually processing your inputs, gaining outputs, and then you actually start back the execution of your queries. What you would do in other graph database, you would spend time on runtime. You actually start your query and then you get results from the first transaction. You process it in app, which is also in memory. You gain the results, then you write back to the database and essentially waste time with round tripping. And here with query modules, everything is executed in one go in Memgraph on the server, and it's optimized for most speed, most throughput, what we are all about as an in-memory database. Let's go back to our query. So graphUtil. So actually what Mage is actually a library collection of all these query modules, but you can also, it also supports your own query modules, which you can embed into an algorithm, into Memgraph, put it and just run it as standalone pieces of code. So it says call graphUtil descendants from Docker. It will actually, I think it will get all the children of Docker. And then we can call graphUtil connect nodes to actually connect our graph. I'm not sure why Memgraph Lab is doing it like this all the time, but yeah, it seems like a bug or something. So yeah, Docker, and then descendants will be all the children of Docker, and then basically we get a directed acyclic graph, which can be quite useful. And so now, if we want to check for vulnerabilities, so actually querying something meaningful regarding cybersecurity, analyzing attack path sequences and so on, we can go actually and do with BFS, see if any of our dependencies, if GQL Alchemy is actually linked to a Python dependency. Mismatched input dependency, but that's not mismatched. Yeah. So yeah, it says actually it does not have any problems, and actually, yeah, we are not vulnerable. What about the other package? It's called vulnerable GQL Alchemy. Yeah, now we have something. So it says vulnerable GQL Alchemy. We have an indirect vulnerability. We have a Pydantic, which is v1.8, and then we have a CVE, which has Python package, Pydantic, and then we have a minimum version, it's only in 1.8. But yeah, this is how you can actually find out your vulnerabilities. non carefully, check all the Pydantic. If we actually go from Pydantic to to its parents, we can actually go back to track it back to vulnerable GQL alchemy, and we'll get the same graph. If you want to show information about Pydantic, we can do so like this. So we show the minimum version, maximum version, and our GQL alchemy also depends on Pydantic. So it has the name Pydantic, but it's different Pydantic. So we'll actually inspect and see if our GQL alchemy has an updated Pydantic version, just to check if there were some how do you say it? If there was something missing from the data, if the data is not if the data is not verified and everything. But yeah, we run here our query, and then we see we have version 132, and it's all fine. It's not marked as vulnerable, and that's it basically. So yeah, basically this was the Memgraph intro into cybersecurity with Python dependencies. As we have seen, we can analyze our dependencies. We can see what's vulnerable, what's not. If we have a meaningful graph, we can see what versions are affected, so we can update our versions. We can, I don't know, do impact analysis. If something is vulnerable and our dataset is updated, let's see. Okay, you need to update this package, and basically that's it. I hope this intro was valuable to you, that you learned something new about Memgraph strengths, about these inline path filtering, about query modules, MAGE algorithms, stuff like that, and that you'll be able to query your datasets more meaningfully and extract insights and provide best value to your business. Thank you all, and see you next time.